All right, let's jump right in. Today, we're going to tackle one of the biggest, most powerful ideas in all of math, the derivative. Now, I know the word might sound a little intimidating, but trust me, it's the secret language we use to make sense of a world that's always changing.
So, it all kicks off with what sounds like a simple question. Think about it. Finding the slope of a straight line? That's easy, right? It's the same everywhere you look. But what about a curve? Its steepness is changing all the time. So how in the world do you nail down the slope at one single infinitesimally small point?
Well, the answer is it's a beautiful idea, really. It's called the tangent line. Picture a line that just kisses the curve at that one exact point, matching its slope perfectly in that single instant. The slope of that line, that's our answer. And that's what a derivative really is deep down. It's a tool for finding the slope of that tangent line.
Okay, so how do we actually find the slope of that tangent line? Well, the first way, the one you probably learned in school, is called the limit approach. And it's a pretty clever trick. It's all about sneaking up on the answer, getting infinitely close but never actually touching it.
See, the problem is you can't calculate a slope with just one point. It's impossible. But what you can do is calculate the slope between 2 points. So we start by cheating a little. We draw what's called a secant line that connects our main point with another point that's super close by. The slope of this secant line, it's not perfect, but it's a pretty good guess for the tangent slope we're after.
Okay, now here's where the magic happens. Imagine you take that second point and you start sliding it closer and closer and closer to the first one. That little distance between them, which we call h, gets smaller and smaller. As you do that, the secant line starts to pivot, right? And it gets closer and closer to looking exactly like our tangent line. The derivative is just what number does that slope approach as h gets ridiculously, mind-blowingly close to 0. That's the limit. And boom, that's the formal definition.
So yeah, this limit approach is the gold standard. It's super rigorous. But yeah, sorry for the pun. It does have its limits. It's not a silver bullet. It doesn't work everywhere.
Just look at a sharp corner on a graph. What would the tangent line even be there? I mean, think about it. If you come at it from the left, the slope looks like one thing. But if you come at it from the right, it's something completely different. There's no single clean tangent line you can draw. So at that exact point, we say the derivative, well, it just doesn't exist.
And this is where things get really cool. Enter one of the titans of calculus, Gottfried Wilhelm Leibniz. He had this, honestly, it was a wild idea. He thought, okay, what if we stop this whole approaching zero business? What if we could just use numbers that are infinitely small, but not actually zero?
So you gotta understand the difference between two kinds of small. On the one hand, you have delta x. That's from the limit world. It's a tiny step, sure, but it's a real measurable number. On the other hand, you have dx. This is Leibniz's creation, the infinitesimal. It's a number so small, it's smaller than any number you can possibly think of. But it's still not zero. It's a bit of a mind-bender, right?
And this is where it gets even weirder, but in the best way possible. These infinitesimals have this one amazing, almost magical property. They are so unbelievably close to 0 that if you square one of them, the answer isn't almost 0, it is exactly 0. That's not an approximation, that's a hard rule in their world. We call it a nil-square infinitesimal.
So let's see this in action. It's going to feel like a magic trick. Let's take a simple function, y equals x squared. Okay, first step. We give x a tiny little infinitesimal nudge, dx. That's going to cause y to get its own little nudge, dy. So now we have y plus dy equals x plus dx squared. Simple enough. Now, step 2. We just do some basic algebra and expand that right side. That gives us x squared plus 2x dx plus dx squared. Still with me? Okay, now for the cleanup. We know y equals x squared, so we can just cancel those out on both sides. And now, the big finale. Remember that crazy rule, dx squared is exactly 0? So poof, it just vanishes. All we're left with is dy equals 2x dx. Last step, we just solve for the ratio dy over dx, and we get 2x. Look at that. We found the derivative with just simple algebra. No limits, no approaching 0, just done.
And this amazing algebraic shortcut isn't just a party trick. It has a really beautiful geometric idea behind it. What it's really saying is that if you could zoom in on any smooth curve, like zoom in so far that you're at the infinitesimal level, that curve would look perfectly straight. They call it the micro-straightness property, and it's the whole reason this incredible shortcut even works.
Okay, so we've got two different ways to find a derivative, the limit way
and Leibniz's cool infinitesimal shortcut. But let's pause for a second. We've been so focused on the how, but what about the what? What does this number, the derivative, actually mean? What does it tell us?
Well, it really boils down to two main ideas. First, the derivative is your instantaneous rate of change. This isn't your average speed over a whole trip. This is the speed on your speedometer at this very second. And second, to make that even clearer, if you have a function that tells you where an object is, its derivative tells you its velocity. Not its average velocity, its instantaneous velocity. How fast is it going right now?
And here's a super simple rule of thumb. Just look at the sign. Is it positive or negative? If the derivative is positive, your thing is increasing, going up. If it's negative, your thing is decreasing, going down. It's really that straightforward.
Let's put this to the test with a real example. Imagine this formula describes the volume of water in a tank. So at 1 minute in, we calculate the derivative and get -12. Negative sign, what does that mean? The volume is going down, the tank is draining. Okay, now let's jump ahead to 5 minutes in. Now the derivative is +4. Positive sign means the volume is going up, the tank's filling. But what about right at the 4-minute mark? The derivative is 0. What does that mean? Well, for that one single instant, the volume isn't changing at all. It's the moment the water level bottoms out and starts to rise again.
All right, this is my favorite part. How does all this abstract stuff about infinitesimals actually, do anything for us in the real world? Well, it turns out it gives us one of the most powerful tools in all of science and engineering, approximation. So back in that weird, wonderful world of infinitesimals, you can prove something that sounds completely wrong. It turns out that for an infinitesimally tiny angle dx, the sine of dx isn't just close to dx, it's equal to dx. I know, it's a mind-bender.
And that bizarre fact from the infinitesimal world gives us an unbelievably useful trick in our world. It means that for any small angle, as long as you measure it in radians, the sine of that angle is so close to the angle itself, you can pretty much just say they're the same. You can literally just ignore the sine part for small angles.
There's a name for this technique. It's called linear approximation. And if you think about what we're doing, it's amazing. We're taking a little piece of a complicated curvy function and we're replacing it with its simple, easy-to-use straight tangent line. See? We've come all the way back to where we started. It's all about that tangent line.
So who cares? Well, anyone who's ever used a clock should. The real physics equation for a pendulum is a total nightmare to solve because of that sine function. But the swings of a pendulum in a clock are really small, so physicists just use our approximation. They replace sine of theta with just theta, and when you do that, the messy equation suddenly becomes simple, and it reveals something incredible. The time it takes for a swing doesn't depend on how big the swing is. Every tick takes the exact same amount of time as every tock. That property is called isochronism, and it is the entire reason pendulum clocks actually work.
And that right there is the whole point. The derivative isn't just some formula you had to memorize for a test. It's so much more than that. It's a language. It's the language we humans invented to talk about change, to describe motion, and to understand the beautiful, dynamic universe we live in.
So I want to leave you with this question. We've seen how the derivative goes from a simple question about slopes all the way to the secret of telling time. If one simple approximation, born from this one idea, could completely revolutionize timekeeping, just imagine what other secrets are out there. What other complex problems in economics or biology or engineering are just sitting there, waiting for us to understand them using this incredible language of change.